Welcome to Center of Math's Advanced Knowledge Problem of the Week. For this week's problem, we want to consider a set S of real numbers such that if we take any finite set x1, x2, xn, that's a subset of S. We have that the absolute value of x1 plus x2 plus xn is going to be less than or equal to 1. And we want to show that the set has to be countable. So the first thing we're going to do, take a one-element subset of S. Note that each element has to be less than or equal to 1. So this set is bounded by some compact subset of R, the set -1, 1, the closed set. So now we're going to consider the complement of the open set -1 over n, 1 over n, in -1, 1, which is it's two closed intervals to the left and to the right with the open set -1 over n, 1 over n. And so the thing we want to note here is that we have an infinite set of points of S, and in any one of these, for any n, we have an infinite point of points of S in this set. And note, we're going to have an accumulation point in here by the Bolzano-Weierstrass theorem. Or even we'll have an infinite number of points in at least one of these closed intervals. And so if we have an infinite number of points in either one of these closed intervals, we'll have, say we have an infinite points in this positive interval, we have an infinite number of points greater than or equal to 1 over n. So we can take x1, x2, xn plus 1, and these will all be greater than or equal to 1 over n, and so we're going to have a set which we're going to add up, and the absolute value of that set that we add up is going to be greater than 1, which we don't want. So we'll conclude that in each of these, the number of points in each set of this form, so S intersected with the set of this form, will have a finite number of points. And so with this information, we can show explicitly how we can count S. So say Sn equals the intersection of S and this closed union of two closed intervals. And so we've established that this has to be a finite number of points for each Sn. And so if we take the Countable union for n equals 1, 2, 3, all the way up to infinity, that countable number of sets, we have a countable number of subsets of S. We're going to take the countable union of these subsets, which is still countable. And note that this countable union will include every point of S except possibly 0. And we're going to add 0 if S includes 0, and it still stays countable. And so S must be a countable set. Thanks for watching. Please check out centermath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.